So today we are going to discuss about current density. We have discussed what is the value of current and how the current is flowing in a conductor, and what is the direction of flow of current, what is the direction of electrons. Everything we have discussed in the previous videos. And here we are going to introduce a new quantity which is called as current density. Here current density is a vector quantity. We have to remember, whereas we have discussed current as a scalar, but current density is a vector. Suppose if you have a conductor and if you consider a particular area, at this particular point you consider an area, and what is the direction of flow of electrons through this considered area considered. And if you say a current is flowing through the conductor, the charges are transferred from one side of the area to the other side. In such manner, if the electrons are moving from one end to another end, what is the direction of flow of charges through this particular area considered? We have to consider this, and this is the area considered here. This area has its own vector, area vector, and the area vector is always normal, and this is the direction of current flow, this is the direction of free electrons, and here the current density is defined as the total current flowing through this particular area considered. So J is equal to I by A, current per unit area, and this area is normal. Here it is considered normal to the direction of flow of charges. It is not essentially it should be normal in all cases. In this case we have considered it as normal because if the area is considered perpendicular, I can write this equation J is equal to I by A. Being a vector quantity, here J is a vector. Definitely J is a vector quantity and A is a vector quantity. So what is the direction of A? Suppose if you are asking the direction of current density, what will be the direction of current density in this case? And in this case the direction of current density is along the direction of current. So this represents the direction of current density. And what will be the direction of electric field? We know the direction of electric field is always from positive to negative. So this is the direction of electric field. So all are acting along the same direction. Current density, current, and the electric field are acting along the same direction. Remember. Okay. Now, here, since J is equal to I by A by definition, I can represent the relation between I is equal to NE A V suffix T, where V suffix T is the drift velocity, and by substituting the values I can cancel this A. This A can be cancelled. So by cancelling this A, the remaining equation is J is equal to NE V suffix T. So it's a vector form. So this represents the vector form equation. Here the current density is a vector quantity. So we must be more careful that the current density is a vector quantity, and this equation is valid only when the direction of current is perpendicular, when the direction of current is perpendicular to the area, and the direction of current density is along the direction of electric field. See, when you consider the direction of the electric field, it is from positive to negative, and the direction of current density is along the direction of flow of current. So J vector and E vector are along the same direction, and it is not that always that J vector and A vector. So these J vector and A vector are acting along the same direction. So we can say the angle between them is 0 degree, or we can say they both are parallel to each other. It is not that always they must be parallel. In this case they are parallel. And suppose if you consider this area, and if the area is somewhat altered, it is tilted. Suppose if the area is tilted like this, and after tilting we can represent the area vector along this direction. So this represents the area vector, and here this represents the direction of j vector as represented here. This represents the direction of j vector, and the angle between them will be theta. And here, when this a vector is resolved into two components, this represents the cos component, so this represents a cos theta. So the direction of current here can be represented. This is the component a cos theta, so this represents the a cos theta component. So the magnitude of the j vector is j, so I can write I is equal to j a cos theta. So this is the very, very important equation. I is equal to j a cos theta. And here, hence the area vector, a is the area vector. A vector is represented as the area vector, which is considered normal to the area. So this current being a scalar quantity, it results in dot product. So the dot product is j a cos theta, and we know for cos 0, if j vector and if this j vector and a vector are parallel to each other, then theta between them is equal to 0 degree. Suppose if theta is 0 degree, we can write cos 0 is equal to 1. So we can write cos 0 is equal to 1. So if cos 0 is equal to 1, definitely then I is equal to j. I is equal to j. So the current is maximum when the angle between them is 0 degree. And we know j is equal to n e tau by m into e vector. This represents the drift velocity equation. From the drift velocity, I can write n e into e becomes e square tau by m into e vector. So j equal to sigma e. So this is also one of the important equation. So j vector is equal to sigma e, represents the direction of j vector is along the direction of electric field, because the conductivity is a constant. Okay. And here the negative sign can be omitted because the current density and the electric field are acting along the same direction, so you can neglect. So here the current density is along this direction and the electric field is also along this direction, so they both are acting along the same direction. So when we compare j and e, the negative sign can be omitted because they are acting along the same direction. And rho is equal to 1 by sigma is called resistivity of the material, which is the reciprocal of conductivity. So this sigma term represents the conductivity, and here this reciprocal of this conductivity is also called as resistivity of the material. Okay. Here this term conductivity is connected with the number of electrons, the charge of the electron, and the relaxation time and the mass of the electron. Here n, e, m, these three factors are constant. Tau is also a constant, but the relaxation time varies with temperature. So if the temperature is large due to thermal agitation, there will be more number of thermal agitation, there will be more number of collisions, and therefore the conductivity of this particular material can be decreased. So the conductivity of this particular material is specified by the motion of electrons inside the conductor and the chance of collision, and the chance of collision is represented in terms of thermal agitation, and due to which the relaxation time, it is connected with the relaxation time. So the conductivity of the material is the degree to which a particular material conducts the electricity. It is the ratio of current density in the material to the electric field which causes the flow of current. I can also write sigma. I can also write the sigma as J vector by E vector. So we can write sigma. This sigma is nothing but, here I can write here, sigma is equal to J by E. So sigma is equal to J by E, which represents the ratio of current density and the electric field which causes the flow of current. So if larger the current density, larger will be the conductivity. Okay, and rho is equal to 1 by sigma, and this is the resistivity of the particular material. Okay. And by knowing this particular equation J equal to sigma E, one can easily understand the concept of Ohm's law. To understand the concept of Ohm's law, this equation is very, very important. J is equal to sigma E, and also I can write J into rho is equal to E. From this equation I can also write J into rho is equal to E. So these are very important concepts, so bear it in mind. In the next video we are going to deal with the Ohm's law. Okay.